indication of what's going on there. I've put, now normally, last time back a long time to when we used to do live meetings in Queen's University, I or Brian Beasley used to do a warm-up talk, and what I do now actually since the lockdown is I do those monthly and I put them on YouTube. You can get to them from our website page, irishastro.org. Anyhow, let's move forwards. Our speaker tonight is Christopher Duffy from Armagh Observatory and Planetarium, and a few other places we saw there on his slide. And he's looking at the Gravitational Wave, Optical, Transient, Observer and Cataclysmic Variables. Chris is a third-year PhD student at Armagh Observatory Planetarium and Warwick University, and he's from Scotland and studied for his undergraduate and master's degree at Glasgow University. And he's worked on a whole lot of stuff, so he's a very knowledgeable guy. So put your hands together, please, for Chris Duffy.
I will just get my screen share.
I'm going to mute everybody, and then I want only Chris to unmute. How about that?
Yes, hold on, I'll unmute.
Everybody is muted. Chris, you are the one allowed to unmute yourself.
Perfect. Right, and I will press play on this. There we go. Okay, hello everyone. I am, as I said, Chris Duffy, and I'm here to talk to you tonight about the Gravitational Wave Optical Transient Observer, or GOTO, and also Cataclysmic Variables. Just as means of introduction, GOTO is a collaborative project between all of the institutions down the bottom that you can see from all over the world. So the UK and Ireland, also out to Australia as well. So it's a truly global piece of work. I know that Paul already introduced me, but I'll just briefly recap. I've just started my third year of my PhD at AOP, but I'm also associated with the University of Warwick. They're ultimately my awarding institution, but unfortunately not been able to get out there much because of the pandemic, but fingers crossed for this year. The bulk of my PhD, this is frozen. There we go. The bulk of my PhD is looking at studying transient objects with wide field survey telescopes, so that are objects which appear in the night sky sporadically, and I'm aiming to look at them instead of specifically targeting them using projects which look at large parts of the sky, and I'm trying to take the data together from those to investigate them. And as such, I'm part of the GOTO consortia, which does that, but also the NGTS consortia, so that's the Next Generation Transit Survey, which is primarily looking to find exoplanets, but it turns out that you can actually use the data to look for other sorts of things, which is really useful because it looks at the same part of the night sky every 11 seconds. So we can build up really good movies of what some of these objects are doing, which can be particularly interesting. So, the Gravitational Optical Wave, the Gravitational Wave Optical Transient Observer, without much surprise, is going to be based looking at events that give off gravitational waves. So a little bit of background on gravitational waves. They were originally predicted by Albert Einstein as part of his theory of general relativity. And essentially what he said was that any accelerating mass can stretch space-time and create waves in space-time. So even me waving my arm back and forward as I'm talking to you now does stretch space-time a little bit and create a wave. The problem is that space is very, very stiff. It doesn't like to move. I say that's a problem. If we were all driving around in our cars and that acceleration was bending space-time, we'd probably rip Belfast apart. But when it comes to being an astronomer, that is a problem. Really, only the most massive events can create waves. So it doesn't move very much, and it's only the biggest events, or black holes, that can recreate these events. So they're very rare. So they're tricky to detect. But how do we actually go about detecting them? They're very difficult, but I'm here talking to you today, so there must be a way. So essentially what we're trying to do, as you might have guessed, we're stretching spaces. We're looking for a change in the size of space caused by the wave. The wave goes and it stretches and compresses space. So the first set of searches back in the mid to late 60s looking for these used large aluminium bars called Weber bars that were a meter or two across. And the idea was as a wave passed through the bar, the length of the bar would change by a tiny, tiny amount. And then using very precise measurements, we'd be able to detect it. Unfortunately, it wasn't successful, and the bars now live in a memorial garden at the University of Maryland. Really what the problem was we need something far bigger than a 1 meter bar. The change is so tiny that it's just not going to show up in 1 meter. So we needed to go back to the drawing board and find something else. And that something else is called the laser interferometer, which, believe it or not, is a very old piece of equipment originally designed in the 1880s to search for something called the ether, which was thought to be what all of space was made up of. Ultimately, the experiment proved that it didn't exist, and the interferometer kind of went into the cupboard to be forgotten about. But come along for the search of gravitational waves, and it finds new purpose. Essentially, what happens is the interferometer measures the difference in travel time for light over the same distance, but 90 degrees apart. So we know that the speed of light is fixed in a vacuum. So you fire a laser to a beam splitter and you send it up to a mirror on one end and to a mirror on the other. It's reflected, it comes back, and it meets at the beam splitter and then is detected. Now, if the length of the length of the arms are exactly the same, no gravitational wave has passed through, then the waves will meet and cancel each other out. But if a gravitational wave passes through, then the arms get changed in length just ever so slightly. And that means that the waves no longer cancel each other out when they meet, and we detect some light. That light is us essentially detecting the gravitational wave. The problem here, though, is that, as I said, space doesn't like to move. So there are very small changes. These arms have to be very, very long because we have to be able to get them long enough that we can detect a change in arm length of that number. I'm not going to make you count the zeros. It's 18 zeros. It's the same distance as 1/1000th of the diameter of a nucleus of an atom. So that's how much we're talking about needing these arms to change by to be able to detect a gravitational wave. It's not easy to get even a gravitational wave to give us that sort of change in length. And this is where LIGO comes in. The Laser Interferometer Gravitational Wave Observatory. You've probably heard of it. It's the famous source of the gravitational wave detections, and it is huge. Each of the arms from that animation that you saw in the previous slide, when put into LIGO, are 4 kilometers long. So it goes 4 kilometers in the direction there, and off the screen, it goes another 4 kilometers. LIGO is actually 2 sites. It's not just this one. There's a site in Washington. I think this is the site in Washington State in America, and another one in Louisiana. They're about 3,000 miles apart. And the reason that we've got 2 is a gravitational wave event travels at the speed of light. So because we've separated the 2 stations by 3,000 miles or so, we can get a rough idea of where the gravitational wave event has originated from. But as you'll hear earlier, that's not a simple problem either. And LIGO, as I mentioned, it was successful. 6 years ago and a day now, the first gravitational wave event was detected. That was the merging of 2 black holes, which had each about 30 times the mass of the sun, so pretty big ones. And as you can see in the figure there, you don't need to take much of the detail, but just if you look at the time axis, you see that the event lasted about 1/10 of a second. These are very short-lived events that make them even harder for us to detect. So you can hear the challenges already building up. But since 2015, we have detected more than 50 of these events, and LIGO has been joined by Virgo, a very similar site funded by the Europeans, which is in Italy, which helps us continue to detect with better sensitivity these events. But for the purpose of this talk, the really exciting detection was on the 17th of August 2017. That was a binary neutron star merger. Now, why is that exciting for us? Because unlike black holes, which you know give off no light, neutron stars are faint objects, but when they collide, their merger does give off light. So in theory, if we know where we're looking, we can point the telescopes on Earth at where the gravitational wave event came from and see the light from there. And in fact, we were able to do that for this detection. The problem, though, is it's not just as easy as looking up. We can't just say it's there. If it was, then there'd be no need for GOTO. The problem, this is going to change slide. It's not changing slide. There we go. The problem is localization. Sorry about that. When you've got the LIGO system looking for gravitational wave events, the area of the sky that we think that the event came from can cover many hundreds of square degrees. So on that plot there, you see a number of the gravitational wave events that have been detected since 2015, and the localization regions imposed on the sky. As you can see, they're pretty big. Now, adding in Virgo, the third site in Italy, does improve it. It gets the ability to localize these events down to maybe 90 square degrees of sky, but it's still quite a lot, particularly when these events, maybe neutron star mergers, last maybe a minute, maybe 10 minutes in our ability to see them. So that leaves large areas of the sky to be surveyed quickly for us to be able to say, that's exactly where the source came from, and allow us to do science on the data. So how do we localize? What do we need? Well, the first thing we need is rapid follow-up. So this figure here shows quite nicely the steps that need to happen. So the various gravitational wave detectors, so LIGO Hanford and LIGO Livingston, the two sites in America, Virgo, the site in Italy. GEO 600 is a smaller interferometer, which is not as sensitive in Germany. LIGO India is another site which will be joining us in 2025, and CAGRA is another which will join us in 2023, I think. What has to happen is we need to get the data from all of them. We need to run it through their computers so that they can say where they think the event came from in the sky. They then need to compare it with theoretical models of what they think different types of events would look like, so that we can select the ones which are likely to have an optical transient counterpart to look at. There's no point in us pointing all of our telescopes to look for a black hole merger. It's not there. We're not going to find it. And then we need to pass it off very quickly to the observers to go and look for it. And all of this has to happen in a matter of minutes as the top. The next thing we need to do, and there we go, is the reliable identification of transients. It's all fine and well being able to cover all of the sky that we think that the event came from, but we need to be able to say confidently what's new. So we use a method called difference imaging. So the bottom plot here shows some data from the ATLAS survey. So that's a team which are primarily looking at supernova. So they build up reference images of the sky. They take many images throughout their runs to make sure they've got an up-to-date catalogue of what the sky looks like. And then when they think they find something, so that's the discovery image, they compare the two of them. Now, by eye, if you and I look at the discovery image and the reference image, they look about the same. The target in the middle maybe looks a bit brighter, but that's about it. But to be sure that we see them, we take them away from each other, and we're left with a difference image. So that shows us what changed between the two images. And you can see very clearly there is a new source there in the middle. So that's how we apply that same technique to looking for events from gravitational waves. But we need to be able to confidently distinguish gravitational wave events from other transient sources. We need to be able to confidently say that this is the event that came from a neutron star merger and not a supernova. So how do we do that? Right now, it's mainly humans going through the data and looking at it themselves and using experience to do it. But as this becomes a bigger and bigger task, it is gradually being handed over to AI to do, and then the best candidates are looked at by humans. So that's what we need to be able to do. And we need a system to do it. And that's where GOTO comes in. It's specifically designed to be optimized for rapid response gravitational wave optical searches. It's a very cost-effective design that can be rapidly scaled out. So if one day we wake up and go, you know what, we would like to add another dome or another observing site, we can do that relatively easy. And its main design goal is to be able to catch these optical counterparts to gravitational wave events early, so we can pass them on to other specialist facilities, so radio telescopes, people who are looking at it in the infrared or gamma ray, for example, so that as a community we can come together and get as much science as possible, as quickly as possible on source. GOTO began its life in 2017 with that first neutron-neutron star merger event, and it has grown since then. Initially, it was a mount with 4 40-centimeter unit telescopes, we call them, the individual telescopes on a mount, and this was increased just before the pandemic, thankfully, up to 8 unit telescopes. Each of these telescopes gives us a 2.8 by 2.1 degree field, and they're each set up with a 5-slot filter wheel, but we're predominantly looking at the sky in the L band. Yeah.
We can now. Leave it on for time.
So you suspected an opposite.
Sorry, but yes, sorry. We're looking at the sky predominantly in the L band, because right now we're not particularly interested in color information, but we will as time goes on. But it's also because our response right now is better in the L band. We can go deeper than we can in the other colors. We can get down to about 20th magnitude in just a 60-second exposure. And taking a whole system together, so all 8 unit telescopes, allows one single GOTO mount to view 40 square degrees of sky at once. So you can see in the plot on the right, that's what one telescope sees in a single exposure. And each mount has 8 of those. So you can start to appreciate that GOTO is able to see a large amount of the sky very quickly. So the prototype is built on La Palma. It is situated on the top of the mountain just there beside the various other facilities that are there. So it's a nice and high site, and the weather is usually pretty good, although it's often very, very cold up the top of that mountain, even when it's beach weather down the bottom. It's designed to operate in all sky mode for the majority of its operations to maintain recent reference images. So that was what I was mentioning about for the difference imaging. If we need to have a recent catalogue of what the night sky looks like, so that we can say with confidence when something new comes along that it is in fact new. There's no point in us comparing an image from 6 months ago when we could compare an image from 3 nights ago to be able to say confidently, this is the new event. It works autonomously, and it's a robotic telescope, and the computer decides what it's going to image next based on a pretty complicated scheduler, which considers various things such as where it's currently pointing, the altitude of the tile that it's looked at. If there is a target of special interest in a tile, it might want to prioritize that over another one. And we've got a dedicated fiber link back to our facilities at Warwick, which allow us to start the analysis of the data pretty much instantaneously, although in reality, it's usually our Australian colleagues who do that because they're awake and we're not, essentially. It's not just gravitational wave events that GOTO is going to be good for. It does have some synergies with other science cases, which I'll talk a bit more about later. But I just wanted to highlight that while it's doing its work, it can be interrupted to go and look at another bright transient that others have seen, or even just serendipitously detect one by itself. And in fact, I think we did, as part of our commissioning, accidentally stumble on a new outbursting cataclysmic variable, but I'll mention that a bit later. So the main part of the prototype operations for GOTO actually ran from March 2019 through to August 2020. So the first half of that was with the 4 telescopes, and the second half was with a full mount of 8 telescopes. And the way that we approach our observing is with a grid of overlapping tiles. So we always come back and view the same set of tiles, so that every exposure of every a given coordinate is always the same field that it's looking at. The purpose being for that is it just makes the difference imaging and comparing night to night observations so much easier. So over that year and a bit that we ran, I think we had a little bit of a close down for the pandemic, but the tiles got viewed on average about 20 times at least. There was a couple there that you see which were above 100, but that was part of stop and stare work as part of the commissioning, that we were wanting to push GOTO. How deep could we go with it, and what was the sort of cadence that you could get out of it and that would work. When it comes to looking for gravitational wave events, we take these tiles and we map them to the confidence region, so where we think the gravitational wave sources come from. And then the scheduler gets to work deciding which tiles to observe and when. So it takes a number of factors into account. So the likelihood that part of the confidence region is the true source of the gravitational wave, but also where it is in the sky. It might decide that it's going to wait to look at a part of the sky because the altitude is too low right now, and if it waits an hour or so, it'll be higher, and it's looking through less atmosphere, and we get better data out of it. So through LIGO 03A, which was the first third of the third run of LIGO, which overlapped with our prototype operations, we actually triggered on 32 gravitational wave events. Now, unfortunately, none of them were binary neutron star events, but it let us practice looking for these events, and it allowed us to tighten up our observing strategy where needed. In addition to that, we also did trigger on 93 gamma ray bursts that the Fermi satellite detected, and it turns out a little bit surprisingly to us, but to others in our consortium not so much, that GOTO is pretty good at looking at that. And we had a paper just come out the end of last month, I believe, discussing using GOTO for following up these events. So following the success of the prototype operations, GOTO was kind of signed off on by the STFC, the funding body, who said, this is great, can you build it? So the La Palma site began its upgrades in June 2021 with a second mount being delivered, which brought major performance upgrades across a whole range of things. The mount was more stable, it reacts better in different wind conditions. The tubes that we actually use for the telescopes are better. They have better light shielding and improved optics, and they can hold their position better. We've got a new drive on the mount, which means we can move tile to tile at 10 degrees per second. Originally, it was only 5 degrees, so we're spending more time observing and less time moving, essentially. And at a stroke, what we did was we doubled the survey area. So you can see there on the top two, the mount, and then as it is installed in the dome in La Palma, and that's actually an image taken at the start of the week, believe it or not, of GOTO deployed looking at the sky. But it isn't just the northern sky that we are interested in. We are looking at the southern sky, and the full design for GOTO will feature a southern node inside Spring Australia. So I think that's about 4 hours outside of Sydney. So you can see our dome arriving off a shipping container at the start of the year, and hopefully, all being well, this time next year, GOTO South will be installed right where that arrow is. We're hopefully getting the foundations laid in the next couple of weeks, and we are waiting for visas to let us into Australia to get to work. Like the La Palma site, this will feature 16 40 centimeter unit telescopes over 2 nodes, over 2 mounts. And that means that the full design of GOTO will be able to survey the entire night sky, north and south, roughly every 2 days or so, given ideal conditions. So you can see the kind of coverage that we have. So we're not just accidentally picked our sites. You can see that Hawaii, Palomar, and Lucia, who are similar sites to ours, they will be involved in transient follow-up, but they're not designed for it, they're not optimized for it, don't see the same parts of sky as us. So GOTO is actually in a really good position to catch these events first and early, but it does also complement the rest of the community. And when fully put out together, what we'll have is a full setup of 160 square degree footprint at any one time with both sites running. So to give you an idea of what that means, you can see GOTO on the right-hand side of that figure. That's one mount from GOTO. We've got 4 of those. And on the left-hand side, you can see the 90% confidence region that was attached to the binary neutron star merger back in 2017. If you imagine in your mind for a second taking 4 of those GOTO sky coverages and superimposing them across the confidence region for the neutron star event, you can see quite quickly where GOTO's strength is. We can very quickly cover the whole confidence region and say, there it is, and we can put it out to the rest of the community to go and study. Now, there's other science you can do with GOTO, as I alluded to earlier. There is a number of different things. It's not just gravitational wave events. One of the easy ones that we're going to be doing and have already done as part of the commissioning work are so-called stop and stare studies. So instead of running GOTO in its all sky survey mode, we might take part of the time, particularly when the gravitational wave detectors aren't running, to do a stop and stare where we pick a star cluster for a month and just look at it multiple times in that month. And that allows us to look at some quite high frequency stellar variability events that you can get in these stars, and who knows, discover potentially the next supernova, but that would be a dream. As I mentioned before, there's other things with gamma ray burst follow-ups that you can do. There's transients and moving objects that we can look at. So that would be discovering by luck a supernova as we're working through our all sky survey work. And moving objects, if a comet comes through our field, well, we're going to take a photograph of it. We're going to have that data, and we can hand that off to the comet people who are always looking for more data on near Earth objects. And who knows, there might be a nice press release on the asteroid that killed the dinosaurs in there. And finally, there's the study of cataclysmic variables, which are something that are quite close to my heart, that I spend a lot of my time working on. And actually GOTO, even the prototype, was able to give me data on to begin to analyze these sources, which is also, and this is also a good point to move on to the second half of this talk, cataclysmic variables. I've mentioned them a few times before, but I expect that, you know, they're not the most familiar types of objects to everyone. So I'm going to get into them a bit and discuss what they are, and then the types of sources that I'm working on and why they're interesting to us. So the basic question, what are cataclysmic variables? They're binary systems which are composed of a white dwarf which is being orbited by a late type star. So think our sun, but 4 billion years down the road. And what's happening is the white dwarf is accreting matter from its companion. It's sucking this matter off, and it forms an accretion disk. So it doesn't just fall in as a stream, it spirals into it. If you imagine the water going down your plug hole, and it just spirals in to the white dwarf and eventually falls onto it. Now this accretion can happen in two different states. There are high states and low states. So as you might imagine, a high state is a high accretion rate and a low state is a low accretion rate. And this manifests itself for us on Earth as we see the system being either bright or dim. This isn't always fixed. Some of them will stay in a high state for lifetimes and we'll never know if they've changed, but some cataclysmic variables move from a high state to a low state every couple of years. And that's giving us an insight into what's happening, and that opens the question indeed as to why is this accretion rate changing? And there's a number of theories surrounding that. There is a third thing that can happen, that the accretion rate can become unstable. And this results in outbursts. So we see that as a transient event. The source suddenly gets much brighter and then fades over time. And this is what happens when the accretion rate suddenly spikes, and then it kind of slowly drops down. And they are kind of particular interest to us because they allow us to get a snapshot into the most violent events and test our theories of accretion under the most extreme conditions. So the first type of source I'm going to talk about are AMCVN systems. So this was actually my first work when I started my PhD at Armagh. They're a rare subclass of cataclysmic variables. Cataclysmic variables are pretty common in the universe, but AMCVNs are not so common. I think at last count, there's actually only about 56 of them that we've discovered. They're hydrogen deficient, helium rich systems. So as you probably know, most stars burn hydrogen throughout their life, and then they die. But AMCVNs, both stars have very little hydrogen in them and lots of helium in them, which makes them simultaneously very easy to identify and quite difficult. On one hand, if you get a spectrum of the light given off by an AMCVN, then you can say very quickly, there's the evidence of the helium, and you can say that's an AMCVN. Unfortunately, they're usually quite dim sources, so getting enough light to get a spectra of it is quite difficult. So it's one of those catch-22 situations. But why are we interested in them? They seem like a lot of bother. There's not very many of them and they're pretty dim. Well, it turns out that they're going to be used as verification sources for LISA. Now, LISA is another gravitational wave detector, but instead of being based on Earth with 4-kilometer long arms, it's going to be 3 satellites which are going to be in space and separated by millions of kilometers. Why is that good? Well, as you kind of got from earlier, the longer the arm, the smaller the perturbation in the gravitational wave that we can detect. So why are AMCVNs these sources? Well, it turns out as they orbit each other, they give off gravitational waves. And because we can see them all the time, we know how they're orbiting each other and we know what they're doing. So we can predict what the gravitational wave events the gravitational wave that it gives off should look like. So when LISA gets launched, we should be able to predict the gravitational wave signal that LISA is going to detect. But we can only do that if we know what these sources are doing in the optical. So that's why they're interested in being studied. So like the rest of the CV population, they have high states, they have low states, and they have unstable states. The high states are the sources which have the shortest orbital period, about 5 minutes that it takes to orbit them. And then there's the low state ones, which are about 40 minutes, which a lot longer. But they're pretty well understood. It's the unstable states that aren't. And that's what I focused on as part of my work. These used to be thought of as a single group that showed pretty similar behaviors. It was thought that orbital period was really the only important characteristic when it came to AMCVNs. That's what determined if it was a high state, a low state, or an unstable state. So why should it be any different for the behavior within the unstable state systems. And what I did, and really that seemed to be the holding thought that everyone had for a number of years, but now there's kind of increasing evidence that that isn't the case. So what I did was I looked at a number of these systems and just showed the light curve. So that's just how the light that we see from these systems changes over time. And these systems all have periods within about 3 minutes of each other. So if the pre-existing theory that the orbital period was the most important thing holds, then they should all look very similar. But I very quickly found out that that wasn't the case. So if you look at the light curves, which are in the red boxes, these are the best examples of this type, you've got very long times when it's bright. It's up at, so for the example, for the first one, it's up at about magnitude 16, and then it drops away and it's quiet at about magnitude 20, and then it comes back up. And that's all that these really do. They also show something called a standstill. You'll see that in the bottom red one, where for apparently no reason, it just decides for a couple of years maybe that it's going to lock itself in a bright state and not do very much. It's not quite as bright as during an outburst, but it's just happy being in a high stable-ish state. And then it goes back to this outbursting behavior. The other ones are the ones in the blue, which show shorter super outbursts, which last about a week, 3 weeks at absolute most, that kind of happen pretty regularly. And you can see that in the blue, particularly the first one. You can see the major events that happen, kind of sharp uptick and then dropping down. But in between these, they also show normal outbursts that will only last a day or two, and it just shoots up. But we don't really know why right now. There's a number of theories that it is to do with the accretion rate and not just the orbital period that's affecting the behavior of that. And it's, I think, an area which is about to get very interesting from a theorist's perspective now that us observational astronomers have turned around and said, actually, your theories don't really fit this. You're going to have to go back to the drawing board. The other type of cataclysmic variables that I've been looking at, and again, they're a more extreme case, are polars and intermediate polars. So unlike the most of the cataclysmic variable population, including AMCVNs, the white dwarf has a really strong magnetic field in these systems. I think I've got 1,000 there, but I think it's actually 10,000 times that of Earth. So an absolutely ridiculous magnetic field. And what happens is this, instead of allowing a disk to form, the magnetic field grabs onto the accreting material and sucks it in as a stream. So you can see in that nice illustration there, it just pulls it straight down onto itself. And because of that, the spin period, so that's the period with which the white dwarf spins on itself, and the orbital period, so the period in which it takes the other star to orbit the white dwarf, actually end up being the same, because it holds on to it almost like a rope as it spins around, as it sucks the material off. The other class of those are the intermediate polars, and these are what happens when the white dwarf doesn't have quite as strong a magnetic field. It's going to influence it, but it's not going to have the same ability to lock things down. So in these cases, as I said, the orbital period and the spin periods don't lock. The white dwarf is still able to rotate at a different rate from the larger donor star. And the weaker magnetic field, it can't pull in the material as a stream. An accretion disk can still form as it does in normal ones, but this disk is truncated by the magnetic field. And that means that when you get closer in to the white dwarf, it can then pull it in onto the magnetic poles as two streams, as you can see there. So the magnetic field isn't giving up. It's still able to influence it, but it's not in the same fashion as it is in a polar. The other thing that can happen in intermediate polars that can't generally happen in polars is that they can outburst. They can suddenly get much brighter. But these are thought to be rare, although the data that I'm currently crunching through does have 3 outbursts in the space of 9 months rather, which could be a new discovery. So watch this space for that. I could be wrong. I could be eating my words in a couple of weeks, of course, though. And we're not really sure why these are happening. They're very short-lived events. They last only a day and a half. And existing theory about accretion says that they shouldn't really happen. It's not possible for them to happen. So we're not really sure what's going on there. And I think that's something that hopefully the work that I'm doing in will be able to probe a little further, and if not answer the question, then ask the right questions for others to follow up on. So I can see that I'm kind of coming up to the end of my time. So I'm just going to leave you with my summary points, just highlighting, GOTO is going to be key in building on multi-messenger astronomy, looking at things in both gravitational waves and electromagnetic as LIGO goes into its next observation run. And we're going to hopefully be fully operational by this time next year. And we're going to be pushing, the limits of what's possible for all sky coverage and depth as we do that. And finally, cataclysmic variables are an interesting class of binary stars which can show outbursts. Not all of them do, and they allow us some pretty interesting extreme tests into our understanding of matter accretion physics that continues to confound us in some parts, but hopefully we'll eventually get there. So thank you for listening. I see there's a couple of things in the chat, but I'll pass back to let Paul direct me.
Chris, thank you. That was absolutely fascinating. For me, there's two contrasting sort of aspects to the two halves of your talk there, actually. And the first of which really struck me was the sheer sort of ingenuity that goes into building machines that detect what are, by the time they get to us, very small measurements to find these things. But on the other hand, in your second part, the sheer scale of the forces of the universe, they're enormous, really, aren't they? One way or another. So and the contrast was quite good. But now there are some questions here. Are you happy to take those for
yes, of course.
Let's go and just open up the chat and have a look. I think it's now what have we got? Terry, you were talking first of all about 40 centimeter telescopes. You want to ask a question to Chris there?
Yep. Chris, fascinating. I'm really glad I asked you to give that talk. I know you're saying there that GOTO will go down to magnitude 20 or 21. Is that in the visual band or what is it?
That's with the L band, so that's a pretty broad visual band, yeah.
Right. But 40 centimeters is not big for a modern telescope.
No, they're really
much better degree of depth of coverage if you increase them to 1 meter, say. Or is that just too expensive?
It's partly a cost, and the other thing that if I bring up the correct slide, is it this one?
You see them there on the mind?
Yes. Hold on, if I get the right figure. Yes. So if you compare it with down the bottom, you've got LSST. So that's, I think it's a 20 meter. It's a huge one that's going in South America, hopefully starting next year. The trade-off with size is the bigger the aperture, the smaller the field of view that you can eventually get. And GOTO's primary goal is not necessarily always to get the best data on what a transient source is doing, but to see where a transient source has come from and then pass it off to, for example, LSST. It's a much smaller field of view, but I think they're expecting that to be able to get down to color-specific magnitudes of about 25, 26.
Yeah, thanks.
And Terry, you had a second question, didn't you, about the orbital inclination of the AM stars?
The AM CVN stars. I'm I'm just wondering, can you tell the orbital inclination of those orbiting pairs, and would the orbital inclination have any effect on how the gravitational waves propagate towards us? I'm thinking of a scenario where you drop a stone in a pond, and if you're directly up above it, you see the waves radiating outward, but after a while they get very, very small in amplitude and harder to see. Whereas if you're standing on the shore, you can see those waves propagating towards you. So would it be easier to detect the gravitational waves from ABCVNs if their orbital plane is roughly directed towards us?
Well, I'll start with the first part of the question. Yes, you can. If you have an orbiting binary in the AMCVN, if it is in our plane, it is possible but difficult to identify the orbital period through seeing the eclipses of it. But the precision that you need is usually actually higher than what you need to see an exoplanet.
Right.
Which makes it a little bit hard. We usually actually detect the orbital period by something called the superhump, which is a feature in the accretion disk which is caused by the tidal effects of the orbit,
right.
which I think is about a 10% greater value. But knowing that it's 10% greater, we can make the subtraction and infer the orbital period. As for edge on for gravitational wave events, I don't know is the honest answer how they radiate. I know that we show gravitational waves as two-dimensional, but when they are actually a three-dimensional effect. So I couldn't say. My gut would say that you're probably right, that an edge-on detection is probably slightly easier for us. But yeah, I honestly cannot say. All of the detections that we've made so far have been these merger events, which are violent explosions. Yeah. So the gravitational wave goes out as a spherical event. Yeah. AMCVNs are obviously orbiting, and I can't say if it happens. I can try and find out for you, and if I do get an answer, I'll let you know. But
it's easier to ask the question than to look
yeah.
Right, many thanks.
Okay, Mick McCreary, you had a question about data. Did you want to ask your question to Chris?
Sorry, yeah. Can you hear me?
Yeah.
Yeah.
Sorry, I'm just having trouble there. Yeah, just wondering, how do we actually download the data from a gravitational wave itself? Or are we just relying on the optics afterwards?
So the events that don't give off light, so a black hole merger, for example, the only data that we have on that is from the LIGO detection. And it is essentially all we are measuring there is the change in length of the arms of the interferometer. And then an awful lot of really quite horrible maths is applied to work out how far space has stretched or been compressed by the wave. And then we get the signal out of that. And then having multiple observatories looking at doing this work, we can work out roughly where it came from. And because we've had Einstein's theories around for about 100 years now, there have been a lot of theorists who have been able to go ahead and predict what they think the signal, the stretch and constraining signal would look like from a given type of event. So we can compare it with the theory and say, well, we think this is probably that sort of event. But the actual direct observations, if you think about it in the sense of doing classical astronomy, then you don't really get that out of gravitational waves. It's a very new and different way of thinking about observing the universe.
Okay, it's just that I remember years ago going to a talk and they were saying that this was a new way of observing the universe using gravitational waves. I'm just wondering how is that?
Yeah, so I suppose it's in the same way if you think about looking for an earthquake, you write down, you have the bit of paper that's going along and the needle and the pen. you're not actually seeing the earthquake on the bit of paper that's recorded the earthquake. You're seeing how the earth has been moved by the earthquake. So we're kind of doing the same principle here and recording how much is space being stretched or squeezed by the gravitational wave event that's passed through. So it's, I guess, an indirect observation of what's happening as opposed to a direct observation. So there's kind of a step in the middle that makes it a very different type of astronomy.
Okay, thank you very much.
Okay, Jerry Davidson, you had a question.
Yes, can you hear me okay?
Yep,
Yep.
I hear you.
I was just wondering how rare these events actually are. I mean, are they one or two per galaxy, or can you see them rather like supernovas right across the universe, right across, for billions of light years? So how rare would they be? And with the neutron star mergers or neutron star collisions, do they form black holes? Is a supernova and then a black hole forms after this, or what would happen when these ultra dense bodies collide? What is the result?
Well, I will answer those questions in reverse order. Yes, they do form a black hole. I think I was reading last week that the current existing thought is for about a second and a half, they form a massive neutron star, which then collapses in on itself and forms a black hole. So that is, the outcome of a neutron star merger. The rate of these events, it depends on the sensitivity that we're talking about. To go back and use the analogy about dropping a stone in a duck pond, and the ripple gets less and less. As you go further away from the source of gravitational wave event, the ripple is smaller. So that's why that's why some of the original detectors or gravitational wave detectors didn't detect anything. They were small and they could only detect events that happen close by. As they get bigger, we'll pick up more and more of them. So I think right now we are still, so LIGO's still working in the local group of galaxies. And since 2015, it's detected 50. So maybe that's a rate of about 10 or so a year within about 100 megaparsecs.
My goodness, right. That's some detecting. It really is.
But as we get more sensitive objects, instruments not only will we detect things that are further away, but we'll also detect less violent events that are closer by.
My goodness, right. And it's actually warping space-time, isn't it? It's the ripples of space-time that are. That's the most amazing thing, isn't it?
So we usually if you ever come to the observatory and we're doing something with a demonstration on it, what we usually do is we get a piece of elastic cloth which is strung across a table, and we hit marbles into each other, and you see the waves coming off, and it's a simple demonstration, but it is remarkably analogous to what's actually happening there.
That's fantastic. Thank you very much. A great talk. Absolutely, very indeed, very interesting indeed, and pushing at the very boundaries of research and astronomy and the latest discoveries. So thank you. Very impressive indeed. Thanks. Thank you.
Okay, thanks, Jerry. Thanks, Chris. And Andy McRae had a question.
Yeah, thanks, Paul. As Chris, I think you probably already answered this. Generally, just thinking about where these events occur within the galaxy. Actually, you mentioned there in answer to Jerry's question that they've been detected in other galaxy systems as well. I was, just thinking, how close are we likely to see these? I mean, or CMVs, are they nearby, or are they in globular clusters? I mean, because as
the AMCVNs, the 50 or so AMCVNs that we've detected are all in our galaxy. Yeah. So they're, relatively speaking, nearby. I don't, off the top of my head, have a distance value to give you. So Yeah, but we can definitely see the outbursts, easily enough. And there's something that if there was an outburst happening, you would, or if you knew where to point your telescope, you could very easily detect it yourself. Gravitational wave events, they're going to be a bit harder. Some of them, though, if we do get a close by neutron star merger, then that they can be bright enough for people to detect, but that requires us to be lucky that it happens relatively close by, and it is a bright one.
Yeah, no. I'm just thinking on the back of that, where would you go to look for them, and for your NCNVs or AMCNVs, and also just, I mean, how probable? When we first heard about these gravitational waves, it was binary neutron stars colliding. How probable is it that we're finding these things around the place, and how probable is there likely to be one very close to us, or are they all going to be very remote off?
Yeah, so as for where we'd look, we'd probably stick to just outside of the galactic bulge, because they're faint for the AMCVs, because they're relatively faint objects. Then we don't want to have the rest of the bright population degrading our ability to detect them, because it can be quite tricky. The probability for finding one of these neutron stars events locally isn't great. The Milky Way is a slightly younger galaxy than some other ones, so there's not necessarily been the same amount of evolution, but it's not impossible. As for the binary black hole mergers, in our galaxy, that's definitely quite a low event. I don't think we're thought to have many black holes wandering around our galaxy, but I could be wrong there.
Okay, brilliant, Chris. Thank you very much. Very enjoyable talk. Thank you.
Thank you.
Okay, well, thank you, Chris, and thanks all for the questions. Is there anybody else who hasn't put a question in the chat who wants to ask Chris anything before we thank him very much and let him go for the evening?
Nobody else has one. Can I come in with another one?
What, a third one, Terry?
Right. Nothing to do with what you've talked about so far, but it is within your sphere of interest. Cataclysmic variables, the Z-CAM stars.
Yes.
My favorite. Can you tell us the latest on basically why they stop varying and go into standstill every so often?
Yes, actually, because that's that class of AMCVNs that I mentioned that did the standstills are thought to behave very similarly to Z-CAMs. The current theory that I've read on this is that, as I've mentioned, that cataclysmic variables have high states and low states and unstable states, and it's governed by the accretion rate as to whether or not it is in a stable state or an unstable state. It is thought that for the Z-CAMs, the accretion rate is very, very close to the stable rate of accretion for it to be in a high state. And that every now and then what happens is it just bumps itself up just enough that it falls into the stable state for a number of years, and then for whatever reason, if there's star spots or something, it drops down and then it returns to its unstable state.
Yeah, fascinating. My favorite type of variables. Thanks a lot. An excellent talk, Chris. Thank you very much. And all the questions answered very well too.
Thank you.
Indeed. Well, thank you very much, Chris. We've got no more questions unless anyone wants to nip in for a last one. But otherwise, we'll say thank you very much. You've been a great speaker. You've taken all the questions and answered them all perfectly, which is
thank you,
as good as it gets. So thanks for coming along. Thanks for spending the time with us. And great to see you.
Thank you. Good to see you all. Yeah.
I think yeah, absolutely. We'll give you can sort of clap. You can do a round of applause on Zoom. We'll probably stick around and have a chat for a little while, but and you're welcome to stay if you want. It'll only be
my mouth's a bit dry, so I think I might.
Yeah, it'll only be about the weather and what we've been doing over the summer and stuff. But so thank you very much. We'll see you again sometime, no doubt.
Yes.
Hopefully in person too.
Fingers crossed, yes.
All right.